Hello my friends and welcome to the practical activities of this Artificial Intelligence A to Z course. My name is Adlan de Ponteves. I'm the second instructor of this course who will be doing all the practical activities with you. And the reason I'm starting from this Gmail page is because I want to do everything from scratch so that you don't miss any step while setting up your AI environments. Alright, so as you can see, I literally just created this new email address, artificialintelligenceA2Z@gmail.com, because indeed we will be building the different AIs of this course in Google Colab. And in order to implement code in Google Colab, well, you need a Gmail address. So that's why please make sure to at least have a Gmail address. I just created one. It took me a few minutes so that we can set up Google Colab. And now, why did I choose Google Colab to implement the AIs together? Well, that's for a very simple reason. It's just in order for us to not have to install any packages, because if we implement this, for example, in Jupyter Notebook or another IDE like Spider, we will have to install a lot of packages and this will be a lot of hassle. While if we implement the codes of our AI in Google Colab, well, you will see it's super easy because in Google Colab Notebooks, you will see that most of the packages we'll use are already pre-installed. For example, PyTorch is already pre-installed, which is the framework with which we're going to build our AIs, and many other packages are already pre-installed. And even if we have to install some packages, well, this will be super easy. You will see you basically won't have any trouble getting the required packages to build our AIs. So that's really awesome. If you're a beginner in AI, trust me, we should totally do this in Google Colab. And speaking of Google Colab, well, right before this tutorial, I gave you a link. I actually just copied this link, so I'm gonna paste it right now with you so that I can start from scratch with you. So I'm gonna paste this link in a new tab. Here it is. I'm entering it, and this will take us to the folder containing all the codes of this AI A to Z course. And so it's divided in three parts. Part 1, Deep Q-Learning, containing the Deep Q-Learning code. Then Part 2, Deep Convolutional Q-Learning, containing the code that implements the Deep Convolutional Q-Learning model. And finally, Part 3, containing the code that implements the A3C model. Alright? And of course, right now, we're going to start with Part 1, Deep Q-Learning. And so if you go inside, you will see two notebooks. One with the complete code that implements the whole AI with all the results and everything, and one that contains the partial code, meaning the code not related to building the artificial intelligence. And that's actually going to be our starting point. We're going to open this notebook right now. Please open the notebook and you will see that inside I kept all the code cells that are not related to the core of the AI so that we don't have to re-implement them, like for example installing Gymnasium, which I will introduce you right away. It is basically our playground for building the AIs. Then importing the libraries, right? We will not re-implement this together. This is not really essential. However, everything that has to do with building the AI or training the AI, well, we will implement all of this together so that you really understand how to build an artificial intelligence. All right. So that's what we will do. And then in part 3, as you can see, we visualize the results and that it's not really essential. We don't really have to implement this together. So I left the code in this partial code notebook. Okay. So we're going to have a lot of fun implementing these code cells, to create the architecture of the neural network of this first AI and then training it in these different steps. This will be super exciting. I can't wait to start the implementation. Now, before we finish this tutorial, I just want to introduce you to our playground, which is called Gymnasium. It's an amazing platform where you can build different AIs for different environments. I'm going to quickly introduce you to the essential one. So let's start with the basics. Classic control, that's where you can build an AI, for example, to do the cart pole or the mountain car or the pendulum. Okay, so we won't do that. This is too classic. I want to do something more exciting and advanced. And well, speaking of which, let's have a look at the Box 2D environments, which is what we're going to use for module 1 with the Deep Q-Learning model. Because indeed, with this whole popularity of SpaceX and building an AIs for space, well, I chose the first environment for our first AI to be Lunar Lander. And in this one, as you can see, we'll train an agent, which is this spaceship here, to land properly on the moon, between these two flags here. So this is going to be pretty fun. That's going to be for module 1. Then for module 2, we're going to have fun with the Atari environment. But first, let me quickly show you, the other environment. So you have toy text also, where you can, for example, train a taxi, like a self-driving car, to navigate in a map. Then you have the Mujoko environments, which are pretty cool, but which I covered in another course, so we won't use them for this course. But for example, you can train an ant to walk on a certain field, or a half cheetah to walk, or even a humanoid to walk. This is covered in other courses of ours, so we won't do that in this course. But what we will do is even more fun, in my opinion. You'll tell me what you think. We're gonna train some agents to play the famous and popular Atari games. You remember when we were kids, we used to play those games, and well, that's exactly what we're gonna redo today, but this time with an artificial intelligence. And so, for Module 2, what is the game I chose? Well, let me show you. Let's click See More Environments here. I chose for Module 2. I'm sure you know this game. I'm sure you played it in your childhood, or even still now, because personally I really like it, and I would still play it today. I'm talking about, let's see where it is. I'm gonna scroll down a bit more. I'm talking, of course, about Pac-Man. We're gonna train an artificial intelligence to play Pac-Man in Module 2. And then finally, what did I choose for the last AI we're going to build in this course, the A3C model in Module 3? Well, I chose something that we probably all like. I don't know if you liked the Matrix movie with this famous quote of Neo saying, "I know Kung Fu." Well, in Module 3, we're going to train an AI to be able to say, "I know Kung Fu." Because indeed, the environment that I chose for Module 3 is exactly this one. Kung Fu Master. We're basically going to train an artificial intelligence to be able to fight Kung Fu against another agent. Alright? I hope you're excited about all this. That marks the end of this introductory tutorial on all our practical activities we'll do in this course. And of course, at the end, we'll also have another practical activity for LLMs. This will be a lot of fun because this is the AI of today that you also need to know how to build and how to handle. So there you go. I look forward to now starting the implementation of our first AI for our first module, Deep Q-Learning for lunar landing. Hello my friends, and welcome to this new tutorial of Module 1 on Deep Q-Learning for lunar landing. So in the previous tutorial we got access together to this partial code of our Deep Q-Learning implementation. However, now we're going to start coding, we're going to start running the cells, and therefore it's very important to understand that this notebook here is a read-only notebook. Therefore, you can't make any modification, and that's for the obvious reason that you all have access to this notebook, and therefore no one should modify anything. However, now we will create your own copy of this notebook, which will be created inside your Google Drive folder. And that's exactly why I told you in the previous tutorial that you need a Gmail address in order to use Colab. Because indeed, in order to use Colab, you need to have a Google Drive, which you can only have with a Gmail address. All right? So let's create this copy now. To do so, we simply have to go to File here and then click Save a Copy in Drive. And this will indeed create a copy of this notebook inside your Google Drive folder. I'll show you right away exactly where it is. So actually, if you open a new tab here and then go to your Drive, well, you will see this new folder, Colab Notebooks, inside which you will find, well, this copy of our Deep Q-Learning implementation that you just created in your Google Drive. All right? And this one, you can modify it. And so now what we're going to do is rename this. We're going to remove the copy here because it's anyway now in your own Google Drive. And now if you want, what you can do is create the same structure of the course, with those 3 folders. Feel free to do that if you want to. Or, you can just keep your different notebooks in this Colab Notebooks folder, just like that, okay? Feel free to do however you prefer. And so now we're going to go back to, well, this notebook copy we just created. If I refresh it, it will be renamed Deep Q-Learning for Lunar Landing partial code. And now we can modify it because now it belongs to our Google Drive folder, and therefore we are the owner of this notebook copy. All right, and that's it. Setup done. We can now start the implementation. Not only that, we can also run the cells. And speaking of which, well, that's going to be our first step here. The first cell we have to run is to install Gymnasium, because as I told you in the previous tutorial, indeed, most of the packages are already pre-installed inside Colab, except some of them like Gymnasium. So here, we're going to install Gymnasium. Then we're going to install the Atari environments from Gymnasium. And then same for the box to the environments from Gymnasium. Alright, so this will just install this. I'm going to show you right away that this will work with no issue at all. In order to run the cell, you simply need to click this play button to run the cell. And you will see that it will install Gymnasium and the environments here of Atari and Box2D with absolutely no issue. Let's check it out. Now, as you can see, it's downloading some, dependencies and packages, installing collected packages, Fireman notifications, successfully installed Fireman notifications. Now downloading another license, which is needed for Gymnasium and the different environments. It also downloaded Shimmy, AutoROM, installing build dependencies. You see, you have nothing to worry about. Everything is getting installed successfully with absolutely no issue. Whether you are on a Linux or Mac or Windows, you don't have to worry about, opening a terminal or command prompt and installing the packages that we will use for this course. Here, nothing to do. Everything is fine. Now it's installing the Box2D environments for Python. And in a second, we will have everything, Gymnasium related installed properly for this notebook so that we can build and train our AI in the Gymnasium environments. Now it's almost done, should be done in a few seconds, and then we'll be good to go to run the next cell to import the different libraries. But let's just wait for this to finish. It's going to be finished imminently now. And there you go, successfully built Box2D PY, installing collected packages, Swig Box2D PY, and there you go, successfully installed the Box2D environments and the Atari ones. Alright, so you see, no problem at all. That's the beauty of Google Colab. We just have to run a cell and this installs everything without having to open any terminal or command prompt. Alright, now let's run the next cell, which is about importing the libraries. So let me quickly explain what the libraries will be used for. So this is for the operating system. This is because we will use some random parameters, random variable generators. This is NumPy in order to work with arrays and mathematics. This is of course the Torch library because we will build and train our AIs with PyTorch. Therefore we import the Torch library first, then we import the NN neural network module from the Torch library, then the Optim module for the optimizer when training the AI, again by the Torch library, then functional because we will use some functions during the training, again this is from the neural network module by the Torch library, Autograd, same, another module by the Torch library for the training again, more specifically stochastic gradient descent. Then variable in order to create some Torch variables, we will see that later on in the course. And then finally these modules from the collections library, which will be used indeed during the training. Alright, so let's run the cell as well. In order to do so, we simply have to click this play button to run the cell, and this will import all the libraries. And by the way, as you can see, we didn't have to install any of these libraries. That's exactly what I was telling you in the previous tutorial. All these libraries are already pre-installed within Colab. So we don't even have to do those pip install, right, like we did for Gymnasium, for the Torch libraries, right? That's the beauty of Colab. Here, everything is already pre-installed, so we only had to import them. All right, so that's it. That's it for the setup. Now we are ready to do our first implementation in part 1, building the AI, and more specifically, creating the architecture of the neural network. And well, that's exactly what we'll do in the next tutorial. So are you ready to get your hands on building an AI? If yes, well, join me in the next tutorial where we'll create the architecture of our first AI here, which will be trained later on to land properly on the moon. Hello my friends, and welcome to part 1, building the AI, where we're going to create the architecture of our neural network. Are you ready? Let's do this. So we're going to create a new code cell here, inside which we're going to create a class, which will therefore contain the whole architecture of our neural network, meaning the brain of the AI. So here we go. We start with class, then we're going to name this class network, or you could call it neural network or brain if you want, because it represents the brain of the AI. And then we're just going to use a feature of object-oriented programming, which is inheritance. I recommend to look online if you don't know what it is, which basically allows us to inherit from the tools of another class, which is the module class from the NN module, so that we can build a neural network. All right, so how does it work? Well, we call our NN neural network module, from which we're going to call another class, which is called the module class, which is the class from which we want to inherit all the features of this class. All right, so let's press enter, then let's add a colon, and then here we go. We're going to start, of course, with the init method. All right, just like in any class. And, well, I just pressed enter. You see, that's the assistance of Google Colab. That's good. You probably got the same, so there we go. What do we have to input here in this first argument? Well, it's going to be the state size. What is the state size? That's simply the number of inputs in a state. And to exactly know where it is, well, we have to have a better look at our environment, which I remind for module 1 is lunar lander. We're going to train an AI to land properly on the moon between those two flags here. And well, here is a nice description of the lunar lander environment. What is the action space? Discrete 4. That means that our AI has 4 possible actions that it can play. And then for the input, well, let's see a better description here of the observation space. As you can see, the input state is a state of an 8-dimensional vector, which are the coordinates of the lander in x and y, then its linear velocities in x and y, so that's for its speed vector basically, but we also have its angle, then its angular velocity, and 2 booleans that represent whether each leg is in contact with the ground or not. Alright, so that's the whole observation space, an 8-dimensional vector describing at each time step, well, the state of the AI, the agent, all right? And then we can also see a better description of the action space. I remind that there are 4 actions. The first one is 0, do nothing. The second one is 1, fire left orientation engine, basically move to the left. Then second action of index 2 is fire main engine, basically continue in the same direction. And then finally last action of index 3, fire right orientation engine, meaning move towards the right, all right? So you see better how the action space and the observation space is described. Then we'll have a look at the rewards when we do the training. But for now, we will only need those information of the action space and the observation space. So here we go. Let's go back to our implementation. And therefore, here, as we perfectly understood, well, the state size is going to be 8. But we don't have to specify 8 yet. We will do when we call the network class later on in the training. Alright, then this argument is going to be for the action size, which I remind is, as we just saw, 4, right? 4 actions. And then we're just going to add a default seed of 42, just to fix a seed for the randomness. And we'll see if we use 42 in the future. Then here, that means that nothing will be returned. And actually, you can either choose to keep it or delete it. And then here, next row, well, the purpose of that row is to activate the inheritance. Here, we don't have to specify anything in the init function. However, in super, we're going to enter as argument network and self. And that's just in order to activate the inheritance. All right, and now that's where things get interesting. That's where we're going to start building the architecture of the neural network. But first, we're just going to activate the seed super quickly with self.seed equal, and then we're going to use a function by the torch library, which is going to be manual seed. We're going to find it here. There we go, manual seed. And then, of course, in parentheses, we're going to enter the seed argument that is right here in our arguments. So that's just to generate some random factors. And now, there we go. We start with the architecture of the neural network. All right, so let's do this. Let's start from the first full connection between the input layer and the first fully connected layer. And therefore, the first variable I'm creating here is going to be FC1, representing the first full connection between the input layer and the first fully connected layer. All right, and so how do we create that? Well, we call our NN neural network module, from which we're going to call the linear class, which we can get thanks to the inheritance from NN module. And what do we input in this linear class? Well, first, the first argument is the number of neurons in the input layer, basically the state size. And then the second argument is going to be, of course, the number of neurons in the first fully connected layer. All right, so for the first argument, there we go. We enter the state size. Perfect. And then, now, big question is, what is going to be the number of neurons in the first fully connected layer? Well, there is no rule of thumbs to immediately tell what is the optimal number of neurons in the first fully connected layer. I'm just telling you that there was a lot of experimentation to build a performance AI that manages to land properly on the moon. And the optimal number of neurons that was found for this first fully connected layer is actually 64. All right, but of course, there was a lot of trial and error before finding that optimal number of 64. Okay, and that's it. That's it for the first full connection, FC1, going from the input layer to the first fully connected layer. So now I'm going to copy this. I'm going to paste it just below in order to create the second full connection. There we go, FC2. And so now, according to you, what is going to be the first argument here? Well, that's obviously going to be the number of neurons in the first fully connected layer, therefore 64. And then what is going to be this number here and the next fully connected layer? Well, that depends if we want to have just one fully connected layer or another one. If we want to have just one fully connected layer, then the number here would be the number of neurons in the output layer, meaning the number of actions, meaning 4. Or if we want to have another fully connected layer, well, we would have to specify the number of neurons in this new fully connected layer. And well, actually, again, through a lot of experimentation, trial and error, we realized that the best architecture contains a second fully connected layer, which actually contains, again, 64 neurons. So we actually keep it like that. That's our second full connection between the first fully connected layer and the second fully connected layer. And so now, finally, I'm going to copy this line again and paste it right below. I'm going to call this third full connection, of course, FC3. It is going to have as a first argument the number of neurons in the previous fully connected layer, therefore 64. And however here, what is going to be the new number of neurons? Well, again, the question is, do we want another fully connected layer? And this time, no. Actually, the best architecture contains two intermediate fully connected layers between the input layer and the output layer. So there we go, we stop here, we can directly finish with the output layer containing the action size, and well, therefore, the argument here is going to be action size, which I remind for our lunar landing environment is going to be 4. Alright, but for now we say action size. Alright, and that's it. That's it for the architecture of our neural network. Congratulations, you just built a powerful neural network, which is actually the brain of our AI, which then will return some action to try to land on the moon. So that's going to be it for this tutorial. In the next tutorial, we will make another function to forward propagate the signal from the input layer to the output layer. I can't wait to do that with you in the next tutorial. And until then, enjoy AI. Hello my friends and welcome to this hands-on tutorial where this time we're going to build the forward method inside this network class, which will forward propagate the signal from the input layer to the output layer through our two fully connected layers. Alright, let's do this. So we're going to call this function forward, which is going to take as input, well, first self, and then according to you, what is the main argument that this forward function will call as input? Well, that's of course going to be the state, because it's going to propagate the signal from the state to the output layer in order to play a certain action at a certain time step. All right, so here we go. First, we're going to propagate the signal from the input layer to the first fully connected layer. And how we're going to do that? Well, we're going to use our FC1 object, right? Because this is an instance of the linear class, therefore returning the first fully connected layer. And so right here, I'm going to take this self.fc1, the first full connection. I'm going to paste that here. And of course, it takes as input the state, the current state at a certain time step in the environment. And since fc1 state actually returns the first fully connected layer, well, we're going to create a new variable here, which will contain exactly what is returned by self.fc1 state. Then we're going to have to activate this signal thanks to a rectifier activation function. And to do so, we're going to update the value of x by calling first the f shortcut that we actually imported before when we imported the libraries. It is right here. It is actually the functional module from the NN module by the Torch library, which we shortcut as f. Okay, so that's just in order to call the functional module. And so from this functional module, we're going to call one of its functions, which is the relu function, representing, of course, the rectifier activation function, which takes as input x. And that, meaning these two lines of code, actually propagate the signal from the input layer to the first fully connected layer with a rectifier activation function. And so now we're going to copy this because we're going to do exactly the same for the second part of the forward propagation, meaning from the first fully connected layer to the second fully connected layer. And so I'm copying this. And here, of course, we just have to replace fc1 by fc2. And then, of course, state by x, because the second full connection fc2 takes as input the signal from the first fully connected layer and will return the signal in the second fully connected layer. And then, of course, we keep this. We're going to still activate our neurons in the second fully connected layer with a rectifier activation function. All right, perfect. And now let's take care of the final part of this forward propagation, which is to finally return the final signal in the output layer containing our actions. And to do so, well, we can finish with a return, and then we call our third full connection FC3, which takes as input, of course, X, which is now fully activated with our rectifier activation function through the first fully connected layer first and then the second fully connected layer. And there we go. That forward propagates the signal from the input layer containing the state to the output layer containing our actions, and we're done basically creating the architecture of our neural network. Alright, so you see the beauty of PyTorch? We created this architecture super efficiently. We now have our brain, we now have the brain of the AI, which therefore is able to be trained in part 2, training the AI. So whenever you're ready, let's do this. Now, we're not going to forget to run our cell, right? This beautiful cell we just implemented together. So here we go. We just have to click this play button here to run the cell, and perfect, the cell was executed successfully. Alright, so join me in part 2 to train the AI whenever you're ready, get some energy, and I'll see you super soon to start this training implementation. And until then, enjoy AI. Hello my friends and welcome to part 2 of this implementation, training the AI. We have just built the brain of the AI in part 1, building the AI with the architecture of the neural network composed of 2 fully connected layers between the input layer and the output layer. And now we're gonna train this brain to land properly on the moon. And our first step here will be to set up the environment. That will be a very simple step. So here we go. Let's do this one in this tutorial. So we're gonna create a new code cell. And the first thing we're gonna do, of course, in order to set up the environment, first we have to import Gymnasium, which contains all the environments that I introduced to you in the first tutorial of this module. So here we go. We're gonna import Gymnasium, and we can give it a shortcut like gym. All right. Then, now that we have Gymnasium, well, we can import the environment in which our AI will be trained, meaning the Lunar Lander V2 environment, exactly this one here. So let's go back to our implementation and let's create a new variable which will be exactly this environment. And to get it, well, we first call our library Gymnasium, from which we're going to call a function called make, in which we're going to input exactly the name of that environment. So it's not exactly called Lunar Lander, it is called exactly Lunar Lander V2. That's exactly the name of the environment that you have to enter, by the way, in this make function that you can also see here. You see, you have all the documentation here that can help you if you want to practice, for example, implement this yourself before you watch the tutorial with me. Alright, so let's go back to the implementation, let's paste that inside, and there we go, now we have our environment. The next step, we're gonna get some parameters that we'll need later on in the training, like for example the state shape, the state size, the number of actions, right? Remember when we build the architecture of our neural network, well, we see that it's going to be the arguments of the network class, right? The state size, the action size. So that's actually what we're gonna get right now while setting up this environment. So we're gonna start with the state shape, which is of course this vector of 8 inputs that we saw 2 tutorials ago when I explained to you the observation space and the action space. So here we go, state shape, and to get it, well, we're going to call our environment, the variable env, from which we're going to call this following attribute observation space, from which we're going to get the parameter shape. And that will give us exactly the state shape. And now we have the state shape, that's good, but we also need the state size. So I'm creating a new variable which I'm going to call state size, and which will be exactly, well, the number of elements in this input state, meaning the 8 parameters describing at each time step the state of the environment. Remember the coordinates of the lander, then the coordinates of the velocity vector, etc. Right? We saw that together 2 tutorials ago, and it's also, of course, in this Lunar Lander Gymnasium documentation. So state size, to get it, well, let's be efficient. Let's take this, because actually the state size is going to be the first index of this env observation space.shape. And so the first index is going to be 0, because indexes in Python start from 0. All right. So we're going to do some prints at the end to see that we have the right parameters. Then after the state size, well, naturally we're going to get the number of actions. So let's call this number actions. And then how we're going to get that? Well, it's not going to be with observation space, but of course with another attribute called action space. So we're going to take our environment again, env, from which we're going to call this time the action space. Here it is, action space. And then we just need to add a dot and n to get exactly that number of actions. Alright, we'll do another print later on to show the number of actions, which is of course 4. Remember, do nothing, move left, move right, or keep the same direction while slowing down the descent. And so here we go, that's the parameters I wanted to get for now, which we will use later. And now let's do some final prints to make sure we have the right parameter values. So let's start with the state shape, which I'm first going to enter in quote, state shape. Let's see exactly what it is. And so here I'm separating the string with a comma. And then after the comma, I put the value of state shape, which is of course given by our variable state shape, which we just created. All right, this one, yes. Now let's copy this to do the two other prints. First for the state size, which is of course given by our variable state, well, size. And then finally, let's print the number of actions. So here I'm going to replace that string by number of actions. And of course here, the variable is going to be number actions. All right, we should be good. Let's run the cell to see what happens. We should get 3 prints. Well, before we run the cell, let's actually expect what we're going to get. For this, the state shape, well, we're expecting a vector of 8 elements. Therefore, it's going to be 8, nothing in parentheses. Then the state size, we understood that it is 8, right? The position coordinates, the velocity coordinates, 8 in total. And then the number of actions, well, we perfectly understood that it is 4. All right? So that's what we expect. Now let's run this to see if we're right. And there we go. State shape, a vector of 8 elements. State size 8. 8 input values in each state of the environment at each time step. And then number of actions 4. Perfect. So we're good to go for the next step of this training implementation, initializing the hyperparameters. I look forward to seeing you in that next tutorial, and until then, enjoy AI. Hello my friends, and welcome to the second step of the training implementation, initializing the hyperparameters. So now what we're about to do is simply to create some new variables while at the same time initializing them with a certain value. Alright, so I'll show you. Let's create a new code cell. The first variable we're going to create and initialize is the learning rate. Alright, so that's the name I choose for the variable. And then we're going to initialize its value to 5 times 10 at the power of minus 4. Alright, 0.0005. Okay, now the question is, why do we choose such a value for the learning rate? Well, again, that's after a lot of experimentation, trial and error, to get the best performance at the end when training the AI to land on the moon. Okay, so no rule of thumbs again. This is the best value after experimentation. Next, the next variable is going to be mini batch size, which refers, of course, to the number of observations used in one step of the training to update the model parameters. And so now, is there an optimal value? Well, not really this time. The usual value we choose based on common practice is actually 100. That's a good size of mini batch for deep Q learning. All right? Then, next hyperparameter, the discount factor, also called gamma. So I'm going to call it discount factor just for educational purposes, just to make it super clear for everyone. But if you're used to gamma, you can of course call it gamma. And what are we going to initialize it to? Well, first, let's remind that the discount factor represents the present value of future rewards. So, for example, if we have a low discount factor close to 0, well, that will make the agent short-sighted by only considering the current rewards. However, if we have a discount factor close to 1, well, that will make the agent consider the future rewards in its accumulation of the total reward. And actually, we will get the best performance with a good consideration of the future rewards as opposed to being short-sighted. And therefore, we're going to choose our discount factor gamma to be 0.99. All right, close to 1. Then next parameter, well, that's going to have to do with our next step here, implementing experience replay. I'm talking, of course, about the replay buffer size. And what is that? Remember, that's the size, basically, of the memory of the AI, meaning how many experiences, including the state, the action, reward, next state, and whether done or not, in the memory of the agent. You know, the training to sample and break the correlations in the observation sequences. All right, and I remind that the purpose of that is to stabilize and improve the training process. And so now, what is a good replay buffer size? Well, we're going to choose to store 100,000 experiences in the memory. Let's actually note it like that. Int of 10 at the power of 5. All right, 100,000 experiences stored in the memory of the AI, which will stabilize and improve the training process. Perfect. And now we have one final parameter, which is the interpolation parameter used for the training. So that's the parameter that will be used in the sub update of the target networks. a very important parameter also called tau, but again, for the purpose of this training, I'm going to call it interpolation parameter. All right? But of course, if you're used to tau, you can call it tau. Great, so what is a good value of this parameter? Well, again, after experimentation, after testing several values of this hyperparameter, I can tell you already that the best value, the optimal value to train our AI to land on the moon is actually 0.001, right? Which we can know this way, 10 at the power of minus 3. Alright, and that's it. That's it for the initialization of the hyperparameters. We're now ready to move on to the next step, implementing experience replay. I can't wait to do that with you in the next tutorial, but please make sure to get some energy for it because we'll have 3 methods to implement inside the replay memory class. Alright, so now let's execute this cell and I'll see you in the next tutorial for this next step. And until then, enjoy AI. Hello my friends and welcome to this new step of the training implementation, implementing experience replay. So here we go, let's create a new code cell. We have a lot to do in this cell and we're going to start by creating a new class, which we're going to call replay memory class. That's the usual name we give to the class that basically implements experience replay. And then in parentheses, we're going to specify object, meaning that there's no inheritance this time that we're using, object, and then colon, and here we go. Let's start with the constructor method to initialize the replay memory object. All right, so that's of course the init method, which will take self, to refer to the object, and then another argument which will be capacity, the capacity of the memory. And here we go. So first, we're going to implement a line of code that will be useful if you want to execute this code outside of Colab, for example, on a Jupyter notebook with your machine, if you want to use a GPU. So we're just going to implement this self.device equals, then we call the torch library, from which we're going to call the device function. And then in parentheses, we're going to specify in quotes, CUDA colon 0, meaning we're going to use the GPU if torch.cuda.is underscore available, there we go, is equal to true. Basically, that means that if CUDA by torch is available, then we're going to use the GPU. And then else, we're going to use the CPU. Okay? So that's just useful for if you want to execute this code and make the training faster and more performant using a GPU. All right? Then we're going to take care of the capacity here. So we're going to call our object again self, from which we're going to create the capacity object variable, which we're going to initialize to the capacity argument here, which will be specified later on when we create an instance of the replay memory class. Okay, so we'll see what it is exactly later, but for now, that's how we're going to initialize the capacity variable of our object. All right, so here we go, capacity, which by the way is the maximum size of the memory buffer. Perfect. Then we're going to create a new object variable, which will be self.memory, which is of course the list that will store the experiences, each one containing the state, the action, the reward, the next state, and whether we are done or not. And we're going to initialize that to an empty list, all right, in square brackets. Okay, and that's it for the init method, the constructor method that initializes the replay memory object. And so now we're going to move on to the next method, which will be the push method that will add an experience event into the memory buffer. So let's take a little break here. We'll do that in the next tutorial. And until then, enjoy AI. Hello my friends and welcome to this new tutorial. In this one we're going to implement a new method of the replay memory class which will add an experience into the memory buffer. I remind that we chose our replay buffer size to have 100,000 experiences inside, and well, the method we're about to implement right now is the method that will add those experiences into this replay memory buffer while also checking that we don't exceed the capacity. Okay, so let's do this. Let's start by defining the method, which we're going to call push, and then in parentheses we're going to enter 2 arguments. The first one is self for the object, and the second one is going to be the experience or event, as you want. That's the same thing. It's what basically contains, the state, the action, the next state, the reward, and that boolean done saying whether we are done or not. All right. So push self event and then colon, and then here we go. Let's implement that method. So first, remember that self.memory is initialized as an empty list. So the first thing we're going to do naturally is to append an event into that memory. And so very simply here, we take our memory object variable that was defined in the constructor init method. There we go, memory. And then we add a dot and then the append function that you all know, which is a function that can append, meaning add an element into a list. And what do we want to add into this memory list? Well, that's of course the event, right? State, action, reward, next state, and done. Okay, so that's the first step. But now we must make sure that the memory buffer does not exceed its capacity, after we appended that event. And so just below, we're going to add an if condition saying if the length of our memory, the memory of the object, if this length is larger than the capacity, which is self.capacity, then what are we going to do? Well, according to you, which event should we remove from the memory? Should it be the most recent event or the oldest event? Well, it should rather be the oldest event, right? Because the oldest event is at this point less relevant than the newest event. Okay, so let's delete that oldest event. And to do so, we're going to delete what we want to delete, which is exactly, well, the first element of our memory, meaning the memory of the object. And how do we get that first element? Well, of course, we specify in square brackets the index of that first element, which is, of course, the index 0. All right, and that's it. That's all we need to do in order to implement this push method that adds successfully an experience event into the memory buffer while making sure that the memory buffer does not exceed its capacity by removing the oldest experience if necessary. Okay, so now we're good to go for this second method. So now we're going to implement the third one, which is going to be the sample method that will randomly select a batch of experiences from the memory buffer. So if you want, practice yourself implementing this before we do the tutorial together. And well, whenever you're ready, I look forward to seeing you in that next tutorial to implement this. And until then, enjoy AI. Hello my friends, welcome to this new tutorial, and here we go implementing the last method of this replay memory class, which will be the sample method. Well, we choose to call it sample, which will randomly select a batch of experiences from the memory buffer. Alright, so here we go. Let's define this new method called sample, which will take as input, well, first self for the object, and then batch size, which will be the number of experiences that are going to be sampled in the batch. Okay, so then colon, and then here we go. So first we're going to create a new local variable which we're going to call experiences, and which will contain the experiences sampled in the batch. Alright, and so how are we going to get them? Well, we're going to use the random library from which we're going to call the sample function, which takes as input what, according to you? Well, of course, where do we want to sample the experiences from? Well, that's of course from the memory, self.memory, the memory of our object. Okay, then the second argument, what is it going to be? Well, it's going to be the number of experiences we want to have in this batch, and that's of course the batch size. I'm adding k here because that's this expected argument that we see here of the sample function, and that's the batch size. All right, perfect. So first step done, and now we're going to extract one by one the different elements of each sampled experience. Meaning that, remember, an experience contains the state, the action, the reward, the next state, and the boolean done. And so we're going to extract and stack those elements one by one. All right, so let's start with the first element of an experience, which are the states. And so how are we going to do this? Well, first, we're going to call numpy, from which we're going to call the vstack function that will stack the states and the sampled experiences together, right, by extracting them and then stacking them. And so since it's a function, I'm adding here parentheses, and then I'm going to do a one row for loop. You know this, right? That's like a for loop within a list. So you add a pair of square brackets here, and then I'm going to do this for e in experiences. We're going to stack the first elements in those experiences, and therefore that's of course e of index 0, right? The states have the index 0 in each experience because it's the first element of the experience composed of state, action, reward, next state, and done. Okay? So we're getting all the states for all the experiences that were sampled. However, we must just check that each experience in this for loop is existent. And the way we're going to check this is just with an extra if condition saying if e, the experience, is not none. Alright, and that's it. So at this point we have just stacked all the states together from the sampled experiences. Good, but that's not enough. Now what we also need to do is convert these stack of states into PyTorch tensors, because then we're going to work with PyTorch to do the training and especially the neural network when updating the model parameters through backpropagation, and therefore we need to convert these states here into PyTorch tensors. And so how we're going to do this? Well, we're going to do this with another function from the Torch library. So I'm calling the Torch library first, and then this function is very simply from underscore numpy. And that's exactly what will convert these numpy arrays, because now this is a numpy array. And so I'm closing the parentheses here. There we go. And so now with this torch.from numpy, well, this numpy array becomes a torch tensor, a PyTorch tensor. Okay, then almost done, but we also need to make sure that the data type of these states, now PyTorch tensors, is only float. And that's again in order to give a certain format expected then by the Torch functions and classes that will perform the training. And so to make sure of that, we're just going to add a dot float and then just some parentheses. That will make sure the data type is set as float here. And then remember, because we have our device, whether we are using a CPU or a GPU, we're just going to add at the end dot to self.device, one of the variables of our object. And that's just in order to move this stack of states into the designated computing device, whether it is a CPU or a GPU. All right? And that's it. That's how we stack the states together by making sure they're torch tensors, the data type set as float, and moved to the designated computing device. Perfect. So now we're going to sample the next elements in the experience, meaning next the action. So what I'm going to do is I'm going to copy this line of code, then paste it right below, and then simply replace the states here by the actions, and of course the index here 0 by 1, because the action is the second element in the experience, therefore the element of index 1. And then, however, is or should it be set as a float? Well, no, because remember the actions can either be 0, 1, 2, or 3. There are 4 actions, and therefore it's better to set the data type here as a long integer. All right? So then we're good to go. Then next element, next sample of elements, well, that's going to be the rewards, of course. That's the third element in the experience. So I'm replacing here again states by rewards, and then of course the index 0 by 2. The third element in the experience, therefore the element of index 2. And then for the type, is it going to be a float or a long integer? Well, that's going to be a float, of course. So all good here. Then next sample of elements, well, these are going to be the next state. So here I'm going to replace states by next states, and then the index 0 by 3. All right, the fourth element in the experience, therefore the element of index 3. And then, is it going to be a float? Yes, because you know we have angles, we have velocity values, coordinates, so it's definitely a float rather than a long integer. It's just like the states, basically. Okay, and then finally, let's take care of the last elements in the experiences, meaning the dones. So first I'm going to replace the states here by dones, then the index here by, of course, 4, the last element in the experience, therefore the element of index 4. And then, however, here there's a little difficulty. For the type, it's not going to be directly float. In fact, we have to set the data type first as the Boolean type, which is uint8. And the way we're going to do this is just in between those two parentheses here, we're going to add a dot asType, which is a function that sets a type, a data type. And it is inside this asType function that we're going to specify the uint8 Boolean data type, which we're going to call with numpy. Therefore, I'm adding np here, then dot, and then there we go, uint8. And this, the np.uint8 data type, is used to represent Boolean values before converting them into float tensors. Alright, and for the rest, we're good to go. So now we can just finish this sample method by, of course, returning those samples of elements, starting with the sample of states. Then here there's a little trap. Naturally we want to say the sample of actions, but actually from what is expecting then in the training, we actually have to return the sample of next state. You will see why exactly later. Then the sample of actions, and then the sample of rewards, and finally the sample of dones. There we go, and we're done with the sample method from the replay memory class. So double congrats, not only you implemented that sample method, but also you implemented fully that replay memory class. So now let's execute this cell to make sure we did everything right, and that seems to be the case. Perfect. congrats again, that was a big class to implement. So now we're ready for the next step, implementing DQN class. It's going to be an exciting one. We're approaching very soon that exciting training. I can't wait to show you this and show you the final result. And until then, enjoy AI. Hello my friends, and here we go with this new step of the training implementation, implementing the DQN class. And check this out, we're almost done with part 2 implementation, training the AI. After that we'll have part 3 visualizing the results, which I remind we won't implement together because this is not really essential to knowing how to build an AI. This is just a visualization code, so we won't re-implement this together, but that's great. I can't wait to show you the final result. We are on a very good way to build a powerful AI that is able to land on the moon. So here we go with that new step, implementing the DQN class. So let's do this. Let's create a new code cell, and our first step will be to create a new class, which we're going to call agent, or you can call it AI, or you can call it body, you know, to oppose that to the brain we just made before in the network class. But let's keep the usual names that are commonly used in practice, which is agent. So here we go. Let's create this new class, which we're going to call agent. Nothing to specify in the parentheses, colon, and here we go with the constructor method to initialize the agent object. I'm talking, of course, about the init method. All right, so what is it going to take as argument? Well, first self to refer to the object. Then it's going to take the state size and then the action size, which I remind for our environment is 8 for the state size and 4 for the action size. All right, then let's add a colon, and here we go. So first, the first object variable we're going to create is the same one as we created before, self.device, just to give us the choice if we want to use a CPU or a GPU, for example, if you want to use this implementation outside of Google Colab. So what we'll do to do this efficiently, and because we did it before, we're just going to take this line of code, because it's going to be exactly the same, copy it, and then right here, we're going to paste it. Okay? No need to do it again. We understand how it works. Then, next object variable is going to be, of course, the state size. So remember, this is the argument, but we still need to create the object variable. Whenever we create a new instance of the agent class, well, we need to define those variables proper to the object. And the first one we're going to create now is self.stateSize. And then, of course, it will be initialized to the state size argument that will be entered later on in this class instance. All right? Then next object variable is going to be self.of course action size. So that's the object variable, and then we'll initialize it to the argument action size, which will be entered later on when we create the object, meaning instance of this agent class. And by the way, remember that we already initialized the variable for the action size, which we called number actions, right? This is exactly the same one when we set up the environment. Number actions here is exactly action size, the size of the action space. So if you wanted, you know, to make everything clear and the same names, you could also name the object variable number actions, okay? But it's good to work with several names. At least you know that action size is actually the size of the action space as opposed to the state space. So there we go, self-action size equals action size. Now, according to you, what is the next object variable we have to create? Well, there we go. It's time to do a little bit of Q-learning here. We haven't introduced any Q-learning so far, so now is the time. And so, how are we going to do this? Well, we're now going to create two Q networks, the local one and the target one. Remember, as in deep Q learning. And how we're going to create them? Well, remember, we created our network class before, and so we can just simply create two instances of this network class, one that will be the local Q network and one that will be the target Q network. So here we go, let's do this. Let's start with the local Q network. So I'm going to call it local Q network. And as we said, it's going to be created as an instance of the network class which we created before and which contains indeed those arguments, because remember, it inherits from the module class by the NN module. And actually, since we already provided a default value for the seed, we just need to enter those two arguments. So right here in the network class, I'm going to paste them, and that's it, because these are actually the arguments of the object. All right, perfect. And then remember, we need to add this, meaning two parentheses self.device, in order to move it to the designated device, GPU or CPU. Perfect, and now let's do the same for the target Q network. So I'm pasting the line above, and I'm going to replace local here by target. And it's going to be initialized exactly the same way. Okay, then next step, Now that we have our network, what do you think we should create as an object variable? Something very important for the training of our AI. Do you know what it is? Well, I'm talking, of course, about the optimizer. So the next object variable I'm creating here is self.optimizer, and we will create that object as an instance of the Adam class, which allows to build the Adam optimizer. All right. So the Adam class comes from the optim module, and there we go. From the optim module, I'm calling the Adam class, which will take as arguments first the local parameters, meaning the weight of our local Q network. So we're going to take our local Q network here, self.local Q network. We're going to paste that inside the Adam optimizer, and then we're going to call an attribute of this local Q network, which is parameters, and which are exactly the weights of the network, meaning what we will update step by step to predict better and better actions to play in order to land properly on the moon. So parameters. And then there is one more argument, very, very important for the training, and we can see it here very well highlighted. I'm talking, of course, about the learning rate. All right, so we add here LR equals, well, this will be equal to the learning rate variable we initialized before in this part 2. Learning rate, there we go. Then next step, okay, so we took care of the local and target Q networks and the optimizer, and now according to you, what else do we need in order to implement that DQN class? Well, that's of course the memory of the AI, thanks to, of course, our replay memory class. And so I'm creating this new object variable self.memory, which will be initialized as an instance of the replay memory class, which will of course take as argument, remember, let's have a look again at our replay memory class. It takes as argument the capacity, you know, when we create an object. And what is the capacity? That's something we also initialized before. Here it is. That's of course the replay buffer size, which has a capacity indeed of 100,000 experiences. So I'm copying this, and then inside that DQN class, I'm going to enter it as the argument of the replay memory class. All right, and now we have one final thing to do in this init constructor method. That's just a final object variable we need to define and initialize for the rest of the training, which is the time step. All right, the time step counter, you know, for deciding when, you know, in which moment we're going to learn and update the network parameters. So how do you want to call this? You can call it time step or T step. And of course, we will initialize it as 0. All right, and that's it. That's it for the constructor init method. Now we have all the object variables we need to implement that DQN algorithm. And that's exactly what we'll do in the next 4 tutorials. Indeed, we have 4 more methods to implement here for this DQN class, so we'll do 1 method per tutorial. So I can't wait to see you in the next tutorial for implementing that next method, and until then, enjoy AI.